Hello and welcome. One of the important thing we do as part of data mining is to ensure that the data has been cleaned and it's pre-processed. And that's something which we need to do for every data mining project. And hence, this lecture discusses data measurements and data pre-processing. We'll talk about some terminologies, be aware of them, and then some definitions and some of the techniques that we have to employ as part of the data pre-processing activity. I'll start with data object. It's an entity. So it could be a customer, for example, it could be store items, it could be sales within, let's say, a retail organization. In healthcare, it could be patient name. In university database, it could be students, professors. So this is a data object. It's an entity. It's described by attributes of that data object. Basically, for example, we could look at a certain customer, and then we can determine different attributes of that customer. The data objects can also be referred to as samples, examples, instances. There are different terms that are used. And if this data object is stored in a database, then they're called data tuples. It's just a technical term used within data mining to, to represent or to call a data object. Now, the rows of a database that will be corresponding to the data object, and columns will correspond to the attributes of it. So each row will be, for example, a customer, and each column will be customer's characteristics. For example, age of the customer, gender of the customer, etc. Now, attribute, I just mentioned that it's capturing the characteristics or feature of that data object. We also use nouns like dimension, feature, variable, depending on different fields, different terms can be used for it. Attributes describing a customer object can include customer ID, their name, their address, and the observed values for any given attribute, we call them observations. A set of attributes that are used to describe a given object is called an attribute vector or a feature vector, because we're using multiple attributes, for example, for a customer. So we call that a vector. The distribution of the data involving one attribute, for example, just the age of the customer, is called univariate. But if we are using more than one attribute, so age as well as the monthly income of the customer, then that becomes a bivariate distribution. If we use three, then trivariate, and so on and so forth. So we could be using different attributes, different number of attributes, and therefore we'll have to understand the data in terms of distribution involving all those attributes. Now, attributes can be of different types. We could have nominal attributes. This is basically when the values are symbols or names of things, for example, name of a customer. So this would be some kind of a category. Each value represents some kind of a category, code, or state. And these are also called categorical variables. So there's no meaningful order in terms of these nominal types of variables. So we need to sort of, for example, the hair color of a particular a customer, if that is of interest for a company, it would be something which will be coded as a categorical variable. And there's no meaningful order as in black versus gray versus white, whatever the color might be brown. So that's something which we need to be just looking at in terms of having these categorical representation of the attribute. In computer science, we refer to them as enumerations. Then we can have binary data, binary attributes, 0 or 1. And again, binary attributes can be distinguished as symmetric or asymmetric. Symmetric binary attributes are the ones when both of its states are equally valuable, like male and female, and they carry the same weight. So there's no one preference on one or the other. Whereas binary attribute will be asymmetric when the outcome of the states are not equally important. So positive and negative outcomes of a medical test for HIV, for example. Right? So it could be binary, but it couldn't be symmetric binary or asymmetric binary attribute. Then we can have ordinal attributes, an attribute with possible values that have a meaningful order. So this is different from nominal that we just saw in the previous slide. We can rank order them. So customer satisfaction, they would say 1, 2, 3, 4, 5, 1 being very dissatisfied, 5 being very satisfied. So there is a meaningful ordering there, but the magnitude between successive values is not known. So 1 to 2 versus 2 to 3 versus 3 to 4, is the satisfaction level increasing at the same degree for the customer? We cannot say that, right? So this is something which is what ordinal attribute will be. Ordinal attributes may also be obtained from the discretization of numerical values. So sometimes we have some numerical variables, like we'll be talking about that next. So we want to discretize it. We want to create some categories of them. And so, for example, sales of companies, and we want to put them as high, medium, and low sales. So we know that there is an order, but what is the difference between low to medium, medium to high? That doesn't necessarily have the same sort of clarity. Now, numerical attributes are measured quantities, typically represented by integers or real values. Now, here, numeric attributes can be of two types: interval scaled and ratio scaled. Interval scaled attributes are measured on a scale of equal size units. So, for example, if you're looking at monthly sales, for every month, if we are reporting the sales, so that would be interval scaled attributes. So, month number is equally distributed across time, or just the days in a year. So that's interval scaled attribute, equal size unit. Whereas ratio scaled attributes are ones where there's an inherent 0 point. So here, it's not equally spaced. For example, profitability of a company, you could have loss-making companies, which is negative profit, zero profit, positive profit. So it could range quite a bit. So ratio scaled attribute would be that. Another way to organize attribute types would be to distinguish them as discrete and continuous. And in discrete, we could have a finite set of values or countably infinite set of values, right? So, for example, finite set of values for an attribute could be that we are looking at, let's say, the marital status of a customer. There are finite possibilities there, married, unmarried, widowed, etc. Whereas the number of customers themselves can be infinite. You could always have several customers, and it's an infinite set of values, but they can be counted. So there's something which can be countable, and that's something which we need to be distinguishing. So discrete, they are discrete numbers. When one customer is added, we have a discrete addition to the number, but they're countably infinite set. They can be as many as we end up having customers. The other attribute type is continuous. They can have infinite set of values and are typically represented as floating point variables. Example, gross profits of companies. You can have decimal points, and then that decimal point can go in multiple numbers, values. So that's an infinite possibility of real numbers. So that's something which we call continuous attribute types. Now, when we are cleaning data, we have to be aware of data quality measures. There are different types of quality measures. Accuracy of data is very important. Oftentimes, because of human error, computer error, coding errors, we could have inaccurate data. And as a data mining expert, we need to know how inaccurate the data is. Because if we are working with an inaccurate data, all the predictions are going to be really inaccurate. It will not help an organization using an inaccurate data. Completeness of data, again, an important quality measure. Oftentimes we'll have missing values. Somebody did not report few things, customer did not report few of their characteristics, and there are missing values for them. So that's completeness. Again, more missing values means the quality measure has suffered. Consistency of the data in terms of what the reporting is and what exactly should be the value. So this is something which again we need to be sort of looking at in general, what we would expect for a given, let's say, a customer whether this value that has been reported for that customer is consistent with the rest of the information that we have about the customer. Sometimes that could be a challenge. Timeliness, sometimes we need data in timely manner so that we can take the decision. And if it's delayed, then the value of that data is lost. The quality of that data is lost. For example, bonus for salespeople, if the salespeople have not submitted their performance information until that point in time, we are now having to wait to determine what that bonus would be. So it'll be an issue of timeliness. The quality measure that has been suffered is the timeliness. Then the believability of the data, which again relates to whether people will trust it. If there has been faulty data that has been used in the past, and let's say employees have suffered because of that, going forward, the employee base may not believe that data, right? They will have some trust issue with the data. For instance, in retail, if the store manager is expected to operate based on predictions from a machine learning algorithm that has been developed by the headquarter analytics team, and in the past, there were certain decisions that were taken or made by the algorithm that actually hurt the store performance. Then going forward, there will be challenges with the believability of the data input as well as output that is coming out of it. So that's something which can be a challenge. Then comes interpretability, whether what has been reported in the data, can people understand what is there? For example, salespeople, when they have to look at a data, and in that data there are different accounting codes for certain things, and they have no clue what these accounting codes are, then there's a problem with interpretability of the data, and that also affects the data quality measure. So we have to be aware of these 6 different types of data quality measures and how much the data is suffering because of them, and take some preventive actions before we start engaging in data mining. Now, for instance, one of them that we just talked about is completeness of data. So if we have to handle missing values, which is something where there is some clear guidance that is there. For others, many of the other data quality measures that we just talked about, sometimes it's human judgment that is needed. But for handling missing values, we could ignore the tuple. We could just ignore all the missing cases, but this can be a challenge. If there are too many missing values, then we are reducing our sample quite a bit. And sometimes the missing value could be systematically missing. And if we ignore all of them, then we are systematically biasing the results of the model. So that's also not good. Sometimes we can fill the missing value manually, but today with such large databases and data sets, we really cannot imagine manual filling in as a feasible option. So we don't necessarily have that option oftentimes. You can use a global constant to fill in the missing value. Sometimes they just put 99999 for every missing value for, let's say, sales revenue, and that becomes sort of a code. But sometimes the problem with this is that the machine learning model, data mining model, may assume that actually that is a number, that is a true number for what that attribute is about, and that can create some incorrect predictions. Next comes use a measure of central tendency for the attribute, like the mean of that variable will replace every missing value, or median of that attribute or variable will replace every missing value. Here we have to be aware that if it's a normal data distribution, if it's a symmetric data distribution, then mean becomes a good measure. But if it's a skewed data distribution, we should employ the median, because mean can be quite biased here. So that's another way of doing it, a relatively better way of doing than the first 3 that I just mentioned. Sometimes we have a data set in which there are different classes. So customers with high income, low income, medium income. If we were to take the mean of that entire set of customers and then replace missing values just like that, then we are going to create some challenges, some problems with the data. We can actually make the quality of the data suffer. So sometimes we'll have to create this mean and median for the samples belonging to different classes. So for instance, all the customers that fall under high income category, we'll take the mean and substitute missing values for customers that belong to that category with that value. For medium income customers, we will replace with the mean or median from that class, etc. So this way, I think we are ensuring that we don't, make the data quality suffer. And then finally, using the most probable value to fill the missing value. This is a more advanced approach. Here we could use regression or inference-based tools such as Bayesian formalism or decision tree induction. And using that, we get an output which becomes sort of our estimate for that missing value, and we substitute that. So there are these different techniques that we could be using as part of handling missing values. Now, when we are pre-processing data, we also have to be aware of the statistics for data. These are like the general understanding of the data, which we need to have before we start engaging in more sophisticated models. So we need to know what the arithmetic mean is, which everybody knows, adding all the numbers and dividing by the total number of uh, values that we have there. Or sometimes it's the weighted mean, where the weight could sometimes reflect the significance that we want to give to each value. For example, in sales forecast, demand forecast, we want to give more importance to the most recent sales rather than what has happened 10 months ago. So sometimes we want to do weighted mean of a certain variable or attribute. Then there's trimmed mean when we have extreme values, outliers. Clearly, it's something which does not belong in that data set, but it is there because of potentially the errors that were there in data capture. We want to, it could be because of error, but it could also be simply that there are outliers that are out there and can create some challenges with our actual analysis. So sometimes we want to remove those outliers, high extremes and low extremes, and then analyze the data. Median is the middle value in a set of ordered data values. Again, most of you are familiar with this. Mode is the value that occurs most frequently in the data set for that attribute. So that's something which, for example, in data set, if we have the gender of the customer, and if we see majority of the customers are female, then that's sort of the mode. Or if we have a numeric variable, and in that numeric variable we can see that there is a particular value which happens to be the most observed, like the age. If we see certain age happens to be most frequently observed in that data set, then that becomes the mode value for that data set. And then quantiles, these are points taken at a regular interval of a data distribution. That way, we are dividing the data into equal sized consecutive sets. So the most common is the quartiles, which is 25th percentile, median, 50 percentile is median, 75th percentile, and then the 100th. So that's sort of quantile. It could be of different types. Quartile is one example of that, but there could be others like 10% followed by 20%, etc. But you're trying to divide the data into equal sized consecutive sets. The next statistics for data is 5-number summary, where we need these 5 numbers for any attribute. What's the minimum value? What is the first quartile, 25th percentile? What's the median? What's the third quartile, which is 75th percentile? What's the maximum? So these 5 numbers can sometimes give a lot of information about that data and is often used. And box plot is a popular way of visualizing a distribution to capture these 5 numbers. A box plot looks like this, where this box is the interquartile range. The top of it is the Q3, third quartile. Bottom is Q1, 25th percentile. The line in the middle is the median. The endpoints are min and max, minimum and maximum, and then you could sometimes have outliers also visible in the box plot. And then variance and standard deviation, these measure the amount of data dispersion, right? The range in the data. So variance is essentially looking at each value subtracted from the mean value and then squared. And then we are adding all of them and dividing by the total number of observations we have. So it's a formula that we apply. And standard deviation is simply the square root of this variance. So sigma will be the standard deviation if sigma squared is the variance. Then we sometimes want to capture two attributes and the relationship between them, how much they change together, for example. So covariance and correlation coefficient are often used for that. Covariance helps in assessing how much two attributes change together. Suppose we have two numeric attributes, A and B. It could be anything. It could be the size of the company in terms of number of employees, and B could be the profitability of the company. And then each and a set of n real valued observations, A1, B1. So A1 is the size of company, number of employees in company one, B1 is the profitability of company one, and so forth until AN, BN, which is the number of employees in nth company and profitability of nth company. So this is sort of n real valued observations we have. It's a vector. The mean values of A and B can be calculated. We know what the mean number of employees are and the mean average profitability in that data set is. So that's A bar and B bar, simply adding the numbers and dividing by n. We typically represent that as the expected value of A and expected value of B, EA and EB. So the covariance between A and B is defined as, so covariance AB will be this expression. Every value, every observation is subtracted by the average for AI. Every value is subtracted from the average with the average for BI also. So the number of employees and the profitability of the company, we're subtracting each value with the average and then multiplying the two and then adding all the numbers and then dividing it by the total number of observations. So that's what covariance will be. Now we could have positive and negative covariance if the two variables are changing together. Larger companies typically have higher profits. Then we have a positive covariance. On the other hand, if they are moving opposite to each other, so if one goes up, the other goes down, we have a negative covariance. Now, correlation coefficient is very closely related to covariance. Again, for numeric attributes, we can capture the correlation between two variables and calculate what we call a correlation coefficient. It's also called the Pearson's product moment coefficient. And as you can see, this formula is very much similar to this formula, except in the denominator, we are also multiplying the standard deviation of A and standard deviation of B. Otherwise, the numerator is identical. So that's the correlation coefficient. And this value, again, can have positive and negative values. And depending on positive or negative, we can determine whether the two attributes are moving in the same direction or opposite direction. Now, we talked about dimension reduction earlier. Sometimes we have to reduce the dimension in the data. And one of the ways in which we can do this is principal component analysis. Basically, what we do here is if we have a large number of cases, several customers for which we have a certain attribute, we can, and there are several attributes that we are looking at. For example, we're looking at the age, we're looking at the gender, we're looking at their monthly income, etc. What principal component analysis does is it provides a few variables, sometimes as few as three variables, so three attributes that are weighted combinations of the original number of variables. So for customers, if we have several variables, several attributes, instead of using all of them, we could reduce the number of attributes that we will be using, maybe let's say three. And those three are weighted linear combinations of the original set of attributes we had. But these three attributes retain majority of the information which we had in the original set. So we don't really need to use all the data, but we could use the principal components that we have just calculated or obtained. So that's what we are trying to do. And that way we have reduced the dimension in the data, number of attributes that we need to use. And that way we can actually come up with some good decisions with those limited number of attributes or variables. And finally, data normalization. Sometimes we have highly skewed data sets and variables, attributes. So we need to replace that original variable or original attribute with a standardized version of that variable that does not have that much of skewness, that much of sort of non-normal distribution. So this can be accomplished by various means. We could divide each variable by its standard deviation. Um, that way, we'll give all variables equal importance in terms of variability. Something called standard normalization is often used where each value within the variable is subtracted first by the mean of that variable and then divided by the standard deviation of the variable. This way, we are creating standard normal value for that variable, and then that is used for analysis. And then there could be other techniques like taking logarithm of that value, or sometimes square root of the value. There are different ways in which you could be normalizing. Every time you normalize, you typically would like to take a look at the histogram, look at the kurtosis and skewness within that, and then understand whether the data has been normalized or not. And that way we can make use of many techniques that rely on that assumption. Now, with that, I conclude a discussion on data and various aspects of data, as well as pre-processing data. And I look forward to engaging in other topics as we go on. Thank you.